Okay, so this is chapter 2.6 in differentiation, and it's about related rates. So in the last section, we talked about implicit differentiation. And we always use implicit differentiation when the variable we were differentiating in terms of was somewhere in the equation, even if there were other variables as well. So an example of what we used to do is, okay, so an example equation of something we used to do it was something like we'd have y equals 5x plus y, and we would differentiate in terms of x. So in that case, if I was differentiating in terms of x, I would do this equation like so, where I would separate the y from the 5x and then also the other y. And because this was in terms of x, I'd have to think of it as taking the derivative of y, chain rule, and then taking the derivative of y in terms of x. So that this would sort of cancel out and end up being a d over dx if you think about it algebraically. So then the derivative of this would end up being 1, and then you'd have a dy over dx equals the derivative of that would be 5. And the derivative of that, same thing as before. You take the derivative of y in terms of y, and then by chain rule also do dy over dx. So it would end up being dy over dx equals 5 plus 1 dy over dx. All right, so that's a refresher from the last section. Well, what would happen if we wanted the derivative of this equation in terms of x, but there was no x in the equation, at least that you could see? So what if the equation looked more like this, and we still wanted the derivative of this in terms of x, a variable that's not explicitly in the equation? Then we'd have to still be doing implicit differentiation, but it would look a little different. So that's kind of what this section is about. And we specifically are using it in terms of how things change in terms of time. When we have formulas such as the volume formula that doesn't explicitly have time, but the volume of things often change in terms of time, like the volume of water in a swimming pool that you're filling up. Well, time isn't in here, but in terms of the volume of the pool volume of water in the pool will increase over time. So it's implicitly in there. Okay. So let's take a look. So the first example they talk about here is when your water is drained out of a tank, and the tank is a cone shape. All right, so the volume of water in the tank will be 4/3 pi r squared h, because that's the volume formula for a cone. So the volume formula for a cone is 4/3 pi r squared h. And so in this case, V stands for the volume of water that there is, R stands for the radius of water that there is, and H stands for the height of water there is. And since it's being drained out, that height is decreasing and decreasing and decreasing. And as the height decreases, it turns out that because a cone has a smaller and smaller radius as it goes down, the radius is also decreasing. And because as you go down in height and radius, the volume, if you're going down in height and radius, then you're also decreasing in volume, okay? So we want to differentiate this in terms of time, right? So implicitly, there's time in here, but explicitly, there is no mention of time. So that means I'm going to, if I think of it out in terms of chain rule, it's d over dt of the volume equals d over dt of pi over 3 r squared h. So this side, if I were to show the implicit variation going on, would be dv over dt equals, and then we're going to do the product rule. So we're going to do pi over 3 r squared times the derivative in terms of time of h plus pi third over 3 times h times the derivative in terms of t of r squared. They took the pi over 3 out completely so that they didn't have to deal with that at all. So you can do that as well. You'll get the same answer. So then the derivative of this in terms of time, we're going to have to use a chain rule. So that's going to be derivative in terms of h of h times the derivative of h over derivative of t plus pi thirds h derivative in terms of r squared times derivative of r over dt. If I squish that in there. So let's also put that pi over 3r squared in front of there just to keep that consistent. So then this is going to be 1. So I don't have to put that there. And then there's going to be times dh over dt plus this is going to be 2r times dr over dt. This then becomes 2rh times dr over dt with the pi over 3 in the front. And I'm purposely leaving the pi over 3 in the front here because I want you to see that we end up with the same answer as they do, only they factored out the pi over 3. So when you factor out pi over 3, you're left with r squared dh over dt, which is this right here, plus 2rh times dr over dt, which is 2rh times dr over dt. So it's the same formula. All right. So let's take a look at another example. Try and think about this problem without looking at the solution. I know it's kind of there, so I'll even move this down a little so you can see all of it. And the question here is, the variables x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. They want you to find dy over dt, and they give you some information. The information they give you is that x equals 1, and they also give you the information that dx over dt equals 2 for that particular value or coordinate point that you care about, which is when x equals 1. So we're first going to take that and we're going to find the differentiation of it in terms of t. So I'm going to copy the equation. Then we're going to find d over dt of y equals d over dt of x squared plus d over dt of 3. But the derivative of a constant is always 0, so that's going to end up just canceling out right here. All right, so the derivative of this in terms of t, we're just going to leave it as dy over dt. This one, we're going to have to use a chain rule, so derivative of x squared in terms of x times the derivative of x over dt. So this is going to be 2x, and then we're left with dx over dt. Excuse me. You should be able to finish this on your own by now, plus 0. So I encourage you to pause the video and finish this. All right. They asked for dy over dt. So this is already isolated on the left. That's pretty nice and convenient. They told me that x equals 1, so I can plug in 1 for x. And they told me that dx over dt is 2, which is also nice. So 2 times 1 times 2 equals 4. So my answer is going to be the change in value of y in terms of t is equal to 4. So change in y per unit of change in time equals 4. All right, let's do another example. In the next example, they are not going to explicitly give you the equation. So but they are going to give you all the information necessary to find that equation. All right. So here's example 2. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles, as shown in figure 2.34. That's this picture over here, right there. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. All right, so that's dr over dt right there. So I'm just going to write that down as information for example 2. The change in radius over change in time is equal to 1 foot per second. As soon as you see the word per, you know that it's a rate. All right, and if it's a rate, you can, a rate is what derivatives find. That's exactly what derivatives find. So you know that if it's as soon as you see the word per, it's a rate, and as soon as it's a rate, you can write it in terms of some sort of derivative. When the radius is 4 feet, all right, so radius equals 4 feet. At what rate is the total area of the disturbed water changing? So they're asking for the rate of change of the area. Okay. Well, the area of a circle you have to have memorized. So that's pi, yeah, a equals pi r squared. So we're going to start with that. And then we're going to find the derivative of this in terms of time. So it's going to be d over dt of a equals d over dt of pi r squared. So this one, we're just going to write as dA over dt. This side, we're going to write as d derivative of this in terms of radius, and then by chain rule times the derivative of the radius in terms of time. This is equal to 2 pi r, since the derivative of r squared is 2r, and then you need to put that 2 in front of the pi, times dr over dt. Well, at this point, they were asking for the derivative of the area in terms of time, which I already have isolated on the left. They gave us what the radius was, so I can plug that in. And I do recommend that you pause the video at any point, like if you haven't already, and see if you can finish this problem off. And then the derivative of the dr over dt is equal to 1, so I can plug that in for dr over dt. So 2 times pi times 4 times 1 is going to be 8 pi. So that means that the change in area over time is equal to 8 pi feet squared, since they're doing the radius in feet in terms of feet, per second, since that was the unit that I could see that they used for time right there. If they want an estimate, you can plug in pi there. I'm going to use the pi button to get the most accurate answer there. So I'm not using 3.14, I'm using the pi button. And if I multiply that by 8, I get 25.133. And I'm going to round it to the nearest thousandths place. Okay. And let's see if that matches there. They did, in fact, have the same answer. Okay. Guidelines for solving related rate problems. The first thing is you want to identify all given quantities and quantities to be determined. Sketches are also helpful. Labeling quantities is also helpful. So that's what we did here. We labeled what we knew. As soon as I read it, the problem, I labeled all the numbers that they gave me, and then I labeled what they wanted me to solve for. So I could keep things straight. If the problem were, say, a lot longer than this, it's a good thing to do so you don't get lost. Step 2, write an equation involving the variables whose rates of change either are given or are to be determined. So we need an equation, and it needs to use either what radius or time, since those are the given quantities. So they gave us the radius and they gave us the derivative of the radius in terms of time. They also asked for area, so you know that there's going to be an area formula likely to be involved in the situation. Step 3, using the chain rule, implicitly differentiate both sides of the equation with respect to time. Number 4, after completing step 3, substitute into the resulting equation all known values for the variables and their rate of change, then solve for the required rate of change. All right, so let's try that again. We'll take a look at that later. But we'll try that again with this example with the inflating balloon. All right, so again, here's where you should pause the video and see if you can figure this out on your own. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. All right, so the given information would be rate of 4.5 cubic feet per minute. As soon as you see cubic feet, you know it's volume. Okay, so you should have it memorized that square feet is area or surface area. They're both a type of area. And any unit cubed is going to be volume. So that could be a key word in case they don't actually use the word volume or area, like in this case. Okay, so that means that the air being pumped into the spherical balloon is changing the volume of that spherical balloon. So it's a sphere, so you should have the volume formula of a sphere memorized. So the volume of a sphere is going to be 4/3 pi r cubed. The rate of change of the volume in terms of time equals 4.5 feet cubed per minute. And they want to find the rate of change when the radius is 2 feet. So they're looking for the rate of change of the radius in terms of time. So that's what they're looking for. So this is my equation that uses volume, which is some information that they gave me, and it uses radius, which is what I'm trying to solve for. So now I'm going to differentiate in terms of time. That's the next step. dv over dt equals d over dt of 4/3 pi r cubed. There is no t in here, so I'm going to rewrite this in terms of the chain rule. So derivative in terms of the radius of this whole thing times the derivative of the radius in terms of time, or over. Okay, so the derivative of this in terms of the radius is going to be 3r squared for this section. So I'm going to do 4/3 times pi times 3 r squared. R, 3 and 3 cancel out. That's going to be 4 pi r squared times derivative of r over time. They want us to find for the derivative of the radius in terms of time. I'm going to go ahead and plug in dv over dt at this time because 4.5 is easier to deal with than those variables, right? So dv over dt equals 4.5, so I plug that in. Radius is also 2, so let's plug that in as well. So this is 4.5 equals 2 squared. 2 squared is 4 times 4 is 16, so that's 16 pi. So I'm going to divide both sides by 16 pi. So the derivative, the rate of change of the radius over time is equal to 4.5 over 16 pi feet per second. And if I go ahead and make sure that I put that in a calculator correctly, so remember in a calculator, you'd have to put 4.5 divided by parentheses 16 pi, close parentheses. Would end up being roughly 0.0895 feet per second. So they rounded it as 0.09. In example 3, so I use 3 decimal places because in the AP exams, it should be to the 3rd decimal place unless otherwise indicated. All right, in example 3, note that the volume is increasing at a constant rate, but the radius is increasing at a variable rate. So the air is going into the spherical balloon, right, at a constant rate. So it's constantly increasing by 4.5 cubic feet. So the air is going in at the same rate all the time. But the radius is increasing at a variable rate. So dr over dt changes according to the answer for that changes according to what the radius is. So as the radius changes, the rate dr over dt changes. Just because two rates are related does not mean that they are proportional. In this case, they are not proportional because the volume is increasing constantly, but the radius is not. In this particular case, the radius is growing more and more slowly as t increases. Do you see why? So this is an increase in radius that's incredibly slow. And if you think about a sphere, if it's a really small sphere, then when you put a certain amount of air in it, it's going to grow faster. But if they have a really big sphere and you add a little tiny bit of air into it, it's not going to change the radius very much because the radius is already so big. The item is already so big. So that's why that's why the more time has passed and the more air is already in the sphere and the bigger the sphere is, all of those things are related. More time passes, the sphere is bigger, the radius is already super big, then the growth of the radius will decrease and decrease and decrease because the air that fills up that sphere doesn't change. There has to be a whole lot more air to change the radius by a little bit as the ball gets bigger and bigger. Okay. So we're going to take a little brief break from word problems and do a little exercise here. Okay. So as a little exercise, let's take a look at these verbal statements and see if we can kind of identify the information that has been provided. So they're telling us that the velocity is 50 miles per hour. So velocity is a rate. So that means it's going to be change in distance over change in time. And that's going to be 50. And it's been traveling for 1 hour. So that means time equals 1 hour. 50 miles per hour. And remember, again, the word per is a hint to you that you can write it as a derivative. And we want some sort of equation that uses velocity or that uses x. Okay, so we're looking for something in terms of an equation for x. So we're not going to find that equation right now because they haven't given us enough information for us to know which equation to use. But is to figure out what kind of a formula we're looking for and what kind of information they've given us. So try that out for the next problem. All right, so you can pause the video and try this out for these 3 problems. For example, I hope you've done that so far. The water is being pumped into a swimming pool at a rate, they're giving you that this is the derivative of 10 cubic meters per hour. So cubic meters tells me it's the change of volume, so dV over dt equals 10 meters cubed per hour. And so we're looking for some sort of formula for volume. Okay. They did not tell us what the shape of the swimming pool was, so we can't actually figure out what that formula is yet. But again, this is just an exercise. The next one, a gear is revolving at a rate of 25 revolutions per minute. So again, there's a rate word. So this is some sort of a rate in terms of time. So the change in revolutions over change in time is equal to 25 revolutions per minute. Now, revolutions are usually measured in terms of angles. So usually that's not what you're going to be looking for. Although you shouldn't discount it, it may come up. Usually, as soon as you see the number of times something goes around and around, like a gear or a wheel, they're really asking for the change in terms of the angle of revolution. So as soon as you see the word revolution, you should think angle. So the change of the angle over time is going to be 25 revolutions per minute. But in terms of angles, that would be 25 times 2 pi, because every revolution you go around 2 pi radians. So 25 times 2 pi radians per minute would be your rate of change. So you are looking for an equation in terms of theta, the angle of revolution. Okay. All right. Last but not least, let's just clear this space up. A population of bacteria is increasing at a rate of 2,000 per hour. So that means the change in population over time equals 2,000 per hour. So we're looking for an equation that involves the population. And okay, so there was that little exercise to help you kind of set up word problems. And let's now try another one. Speaking of word problems, let's do example 4. An airplane is flying on a flight path that will take it directly over a radar tracking station as shown in figure 2.35. The distance s is decreasing at a rate of 400 miles per hour. So as soon as I see rate, I know that's going to be my derivative. So 400 miles per hour, and it's decreasing, so negative 400 miles per hour. So the change in distance over time is equal to negative 400 miles per hour. And s is distance, not speed. Keep that in mind. And I know that because they said so right here. S equals 10 miles. What is the speed of the plane? The speed of the plane, so they even gave us a little picture here. So the plane is going in the direction of x. So the speed is going to be change in x over time. So that's what we're looking for. They also gave us a picture of the radar and a triangle shape, which was quite nice of them, because then I know that what the equation is that's going to give S, that's going to use S and X. See if you can set this up on your own and pause the video if you haven't already and finish this up. Hopefully you've started this already, because I'm now going to tell you that that equation is the Pythagorean theorem. You've got a right triangle. It's x squared plus 6 squared equals s squared is going to be the equation. I'm going to write that all in one. All right, so hopefully you have paused the video and tried that out, because we are now going to take a look at this right triangle. Hopefully you notice that they marked up 3 sides, so we can use the Pythagorean theorem. X squared plus 6 squared equals s squared. 6 squared I'm going to simplify to 36. And then I'm going to take the derivative of everything in terms of time. So d over dt of x squared plus d over dt of 36 equals d over dt of s squared. That one, I'm going to have to use the chain rule. So d over dx of x squared times derivative of x over in terms of time, plus the derivative of the constant is going to be 0, equals, chain rule again for this, derivative in terms of s squared times the derivative in terms of t of s. So that's going to be 2x times dx over dt plus 0 just disappears, equals the derivative of s squared, which is 2s, times ds over dt. They told us that s equals 10, so I can plug that in. They told us that ds over dt is negative 400, so I can plug that in. So 2x times dx over dt equals 2 times 10 times negative 400. So that's 20 times negative 400 is negative 8,000, I believe. So dx over dt equals negative 8,000 over 2x. All right, so there must be a way to figure out x. Oh, and there is, because they told me that s equals 10, and I have the Pythagorean theorem here. So I'm going to plug in x squared plus 6 squared, which was 36, equals s squared, which is 100, 10 squared, which is 100. 100 minus 36 is going to be 64. So x squared equals 64. Square root it. It's positive and negative when you square root, but we can't use a negative because x is a distance, not a rate. So we have x equals 8. We're going to plug in x equals 8 now to finish this problem off. So that's going to be negative 8,000 over 2 times 8 equals, I'm just going to cancel that out and make that negative 1,000 over 2 equals negative 500. And that was a change in distance, so negative 500 miles per hour. Which is also what they got, luckily. Notice that the velocity has direction. So velocity means speed with direction. So it's slowing down by 500 miles per hour. However, if they ask for the speed does not have direction, so it would just be 500 miles per hour. So the answer technically is 500 miles per hour for the speed. They also gave a note here. Velocity is, an example 4 is negative because x represents the distance that is decreasing. Okay. Let's do one more example. A changing angle of elevation. Find the rate of change in the angle of elevation of the camera shown in figure 2.36 at 10 seconds after liftoff. So time equals 10 seconds. And they're looking for the rate of change of the angle of elevation. So everything's in terms in terms of time here. So it's change of angle of elevation over time. We're going to need to look at the picture and all the information. Let's see if we can use black here. Okay. So the other information, oh, that's hidden there. So the other information they give you is, well, they were kind of generous with that. They shouldn't have had to tell you that. But this picture was very nice. So the camera is 200 feet away from the rocket, and they're calling the height S. And they also gave you an equation here that you're going to need. So television camera at ground level is filming the liftoff of a rocket that is rising vertically according to the position equation S equals 50 t squared, where S is measured in feet and T is measured in seconds. The camera is 2,000 feet from the launch pad. So that means, because I have this equation, that's what I'm going to start with. Because they gave me the time, and I'm going to solve for S. So this is going to be S equals 50 times 100 equals 5,000. So that means S equals 5,000. And it's in terms of feet. Now notice I did not take the derivative of this on both sides, and the reason for that is because the theta was not in here, and they're asking for the change of the change in the rate of the angle. So this is not the equation that they're looking for. They're looking for a different one. And they really gave you quite a big hint there by using tan there. So anytime you have an angle and a side and a right triangle, you can always use a trig function. They gave you a good one to use. So let's go ahead and use their hint. Again, I recommend that you pause the video and try this problem on your own if you haven't already. Okay, so hopefully you've done that. This is S not 5. Let's go ahead and take the derivative of this. So this is d over dt. We're going to have to use the chain rule here. So that's going to be, let's go ahead and see if we can. Let's go ahead and take the derivative of that using the chain rule. So that's going to be d over d theta of tan theta times the change in rate in theta equals, again, chain rule for that side. Derivative in terms of S over 2,000 times the derivative of S in terms of time. All right, so this is going to be secant squared theta this is going to be 1 over 2,000 they told me t equals 10, s equals 5,000, and we're looking for d theta over dt. Oh, so this is another variable we have that we need to get rid of. So this is where we are going to have to find the derivative of that, because I'm looking for ds over dt, and I don't know that yet. They didn't tell me that. So that means that that other equation they gave me, I actually have to take the derivative of that in order to plug it in right here. So let's even use a different color here to denote that we're doing that. So I'm looking for this value, so I'm going to have to use this equation right here. So let's do that on over here. I'm going to find the derivative of that in terms of t. Chain rule on this side, or excuse me, not chain rule. We're just going to do ds over dt equals, no chain rule needed. So I can replace this with 100t. And we even know what t is because they told us that t was 10 seconds. I have that written down. So let's go ahead and plug that in right now. That's 1,000. So we're going to plug that right here and for 1,000. And we're going to do it more neatly than that. And remember, ds over dt ended up being 1,000. Okay, so this is going to reduce to 1,000 over 1 times this. It's going to reduce to 1/2. I'm solving for d theta over dt, so let's pull this over here. Equals 1/2, and I'm going to divide both sides by secant squared, divided by secant squared theta, or times 1 over secant squared theta. And remember, secant squared theta is 1 over cosine squared theta. So we could even, instead of saying divided by secant squared theta, say 1 over 2 times cosine squared theta, which is much easier to look at. So that's what we're going to do. All right. So we now need to solve for cosine squared theta. And before jumping to the idea of 1 minus sine squared, due to the Pythagorean theorem, I'm going to take a look at this picture right here. And notice that this is 2,000 and this is S. So I can actually label this in terms of 2,000 and S. So in this picture, this is because by Pythagorean theorem, this side, if I label it C, S squared plus 2,000 squared equals C squared. So if I'm solving for C, I can square root both sides. Technically, it's plus and negative, except that we're looking at lengths, so we can only take the positive value. So 2,000 squared there. So so the hypotenuse C equals S squared, square root of S squared plus 2,000 squared, which is going to come in handy when I'm looking for cosine of theta. Remember, cosine of theta is what I'm looking for over here. So cosine of theta equals adjacent, which is 2,000, over the hypotenuse, which we just found was square root of S squared plus 2,000 squared. And the reason why that's useful is because we actually know what S is. We know that S is 5,000 feet. We figured that out earlier. So we're going to plug in 5,000 for S here, and you're going to do that on your calculators and figure that out. So 2,000 over square root of 5,000 squared plus 2,000 squared. So I'm getting that cosine theta equals 0.37139. And I'm purposely not rounding it too much because I want my final answer to be accurate to 3 decimal places. So I don't want to lose too many significant digits. So beware of rounding errors. Okay. All right. So I'm going to now go back to this right here where my change in revolution over time, revolution angle over time was 1/2 times cosine squared theta. Cosine squared, I got this value, so I'm going to square that. And I get roughly 0.137931 ... and times that 0.5. And my final answer is going to be 0.069 if I'm rounding to the nearest thousandths place. And it's a rate in change of angle, so it's 0.069 radians per second. And if I So let's take a look at example 6. In the engine shown in figure 2.37, a 7-inch connecting rod is fastened to a crank of radius 3 inches. So here is the 7-inch connecting rod. And here is the handle. The handle we don't need to really think about. Oh, wait, that's not the handle. This is the radius of 3. So this is going around and around counterclockwise. So that's the opposite direction. So it's going around and around and around this way. And so this radius of this circle is 3 inches. So radius equals 3 inches. We need to know. And constant rate of 200 revolutions per minute. So that means d theta. So revolutions, remember, are measured in angles or radians, excuse me. So this would be 200 times 2 pi, because 1 revolution is 2 pi radians in terms of angle degrees. So times 2 pi radians over 1 minute. So that's going to be 400 pi radians per minute. Theta equals pi over 3, because they say so. And then you're really going to need this diagram to understand what's going on. So they want this speed right here, because that's the speed of this piston. So this crankshaft is pushing the piston back and forth, back and forth, back and forth. They want the velocity of the piston moving back and forth. So this right here in the triangle is the piston. So dx over dt is what they're looking for. This is the radius of the circle. Something is cranking this circle round and round. And every time this circle goes round and round, this thing pushes back and forth, back and forth, back and forth, so that the piston moves back and forth, back and forth, back and forth. So that means that these 3 things are related in terms of theta. So I need some sort of equation that's going to relate x with theta, because they gave us the derivative of theta in terms of time, and they want the derivative of x in terms of time. So that would be the law of cosines. So that would be a squared plus b squared minus 2ab cosine theta equals c squared. Oh, they wrote it like this. Same idea. Whatever side you're looking for, so we're going to have to do it in terms of 7, because it's always the side that's opposite the angle you're looking for. So in this case, in my case, angle theta has to be related to c. So this has to be theta, this has to be c. And then it doesn't matter which one we label A or B, because A and B are just the other 2 sides. So then we're going to do x squared plus 3 squared minus 2 times x times 3 cosine theta equals 7 squared. I'm going to simplify that first. So x squared plus 9 minus 6x cosine theta equals 49. All right, so let's find the derivative of this in terms of time. The derivative, I'm going to do the 49 because that's nice and easy. The derivative of any number is always 0, so we can get rid of that. This, we're going to have to use a chain rule, so d over dx of x squared times dx over dt. This is going to disappear, so I'm just going to, because the derivative of any number is just 0, so that's just going to be plus 0 minus 6 times the derivative of x cosine theta. And that's going to take the product rule. Let's do this one first because that's easier. So that's going to be dx times dx over dt. I'm just not going to write that 0 anymore. Minus 6. Now let's do this using the quotient rule. So the product rule, excuse me. So that's going to be derivative of x times cosine theta plus x times the derivative of cosine theta equals 0. Minus 6 times cosine theta and the derivative of x has to use a chain rule, so d over dx of x times dx over dt. So if I just do that, the derivative of that is 1. If I do just that, that's the derivative of that is 1. So that's 6 cosine theta. That's going to be 1. So that's just going to, I'm not even going to write that down anymore since that does not change anything. Times derivative of x in terms of time. And then let's do this. Plus, make use of those colors. We'll do this right here. Plus x. And then we're going to have to use a chain rule for that. So that's going to be derivative in terms of theta of cosine theta times the derivative of theta in terms of time. The derivative of cosine is negative sine theta times derivative of theta over time equals 0. Okay, so to use a chain rule for this part right here, that's going to be plus x times the chain rule, so d over d theta of cosine theta times d theta over dt. So the derivative of this is going to be, of cosine theta, is going to be negative sine theta, and then derivative of theta in terms of t. And then we just add the equals 0 at the end. And all of this in the beginning, which I do not feel like rewriting right now. What I'll do instead is make sure that we remember that this 6 applies to everything in that parentheses. So this is a 6 cosine theta over here. And this is also plus, when I distribute that, this will also end up being plus 6x times negative sine theta times d theta over dt. We're solving for dx over dt. So we're going to want to cancel, get rid of this term right here and move it to the other side. In fact, I will actually write this just for the sake of clarity. I'll rewrite it. This whole thing together, the derivative of x in terms of x is just going to be 1. So that's going to cancel out to 1. So that's minus 6 cosine theta times dx over dt plus, oops, let's not even do plus. 6 times negative sine, negative 1. Let's actually make that a negative 1 times. This is 6 times x times negative 1 times sine theta. So I'm going to do 6 times negative 1 and get negative 6 in the front. Put the x next, put the sine theta next, and put the d theta over dt last. Equals 0. I'm going to add 6x sine theta d theta over dt to both sides of the equal sign. That's going to get me 2x dx over dt minus 6 cosine theta dx over dt equals 6x sine theta d theta over dt. Hang in there. This is a stamina game here. All right, I'm solving for dx over dt, so I'm going to factor that out of this section right here. So I'm going to factor dx over dt out. I get 2x minus 6 cosine theta equals 6x sine theta times d theta over dt. I'm going to divide both sides by 2x minus 6 cosine theta. That cancels out, and I now have dx over dt equals 6x sine theta d theta over dt over 2x minus 6 cosine theta, if you can read that. All right, it's now plug and check. Okay, so d theta over dt, they told us in the very beginning, we figured that out, was 400 pi radians per minute, and the angle is pi over 3. So let's plug those in. 400 pi radians and pi over 3. So this is 400 pi radians, so we're going to replace that. We're going to replace this with 400 pi. Sine theta, remember theta is pi over 3, so we're going to actually put theta right here. Theta equals pi over 3, which is the same thing as 60 degrees. So the triangle will look like 1, 2, root 3. Sine is opposite over hypotenuse, so that's root 3 over 2. So that will be root 3 over 2 right there. Cosine of theta is adjacent over hypotenuse, so that's 1 over 2. So that's going to be 1 over 2. So then I'm going to go ahead and simplify this. That's going to cross cancel with that to become 200 pi. We're going to multiply 6 times 200 pi. To be 1200 pi root 3 over 2x, 1200 pi root 3x. Don't forget the x there. And on the bottom, 2x minus 6 times 1/2 is 3. So much simpler looking, but I still need to find out what x is. All right, let's do it. So we're solving for x. We need to find out what x is. If we go back all the way to this law of cosines formula right here, we can solve for x. So I'm just going to copy this equation down, but simplified. So x squared plus 3 squared is 9, minus 2 times 3 is 6, times x, times cosine theta, which we already figured out down here. Cosine theta, remember, was 1/2 because angle's pi over 3. So we can plug that in right here. Equals 7 squared, which was 49. This is 6 times x times 1/2, so I'm going to do 6 times 1/2 to get minus 3x. I'm going to subtract 9 from both sides. So x squared minus 3x equals 40. And then I'm going to realize that it's an x squared equation. I want to solve for x. So I'm going to subtract 40 from both sides to get 0 on the other side. And then I need to factor. So two things that multiply to negative 40. Negative 4 times 10 isn't going to work. Negative 5 times 8 is almost going to work. Just need to flip the signs so that they add to negative 3. So my factors are going to be x plus 5, x minus 8 equals 0. I'm going to set x plus 5 equal to 0. Subtract 5, so I get x equals negative 5. Same thing for the x minus 8 equals 0. So this is very messy. Let's fix this. This is a 0 right there. Subtract 5, subtract 5. So x equals negative 5. Same thing for that one. So x equals 8. We're going to take out the negative 5 because you can't have a negative side in a triangle. So the answer for x equals 8. So this is what I'm going to plug in to this x. So that's going to be 1200 pi root 3 times 8. Oh, come on. Oh, and that just disappeared. Isn't that just wonderful? All right. So pardon the messiness here. Unfortunately, this is now very difficult to read because it's all jammed over. So I'm just going to see if I can fix this. So 1200 pi root 3 times 8 all over 2 times 8 minus 3. There we go. Because I replaced the x's with 8s. So those were the x's originally. All right. So now the bottom is going to be 16 minus 3, which is 13. The top is going to be 1200 times 8, which is 9600 pi root 3 over 13. And 9600 divisible by 13. It is not. So this would be my final answer if we need an exact answer and we wanted it, how fast the piston is moving. So it's going to be inches per minute, I believe. Let's just double check those units. Yep, inches, minutes. So that's going to be our final answer. If you want to round that to the nearest thousandths place, it's going to be 9600 divided by 13 times pi times square root 3 is equal to 4018. 0.263 inches per minute.